So welcome back, and here we are going to take a look at the second data set and guess the distribution. So similar to the previous data set, we'll use the same steps like doing the descriptive statistics followed by visual inspection and then moving on to statistical test. So without any further delay, let's look at the data set. So again, as usual, we have a single column. So this time we have around 49 counts, which means that we have 48 observations and one header, right? So I don't think we can derive a lot of insights from this Excel file. So therefore, let's load it on to the Google Collaboratory and then start with the descriptive statistics. All right. As usual, the regular formalities, which include importing NumPy and pandas, reading the Excel file, printing the Excel file, right? So we have 48 observations. And then the first step is histogram. Molo, over to you.
Yeah. So this histogram looks very appeasing to the eye. Why is that? Because it has one huge building, one skyscraper, then a couple of skyscrapers on the side, and something to the extreme right. So the first order of business is this is somewhat Gaussian in nature that we can by default fix in our head. Okay. So there's one peak, a couple of peaks around it, and one side. The important thing to note in this histogram is that side bit that is sitting between 90 to 100, right? So that is actually inclining towards something. It is telling us that there are more or there are significant number of observations that are towards one side, which means the distribution is having a tail which is on the right side. So that is something interesting from this histogram. Apart from telling that it could be a Gaussian, it is also telling that it could be a Gaussian with a right tail.
So whenever we see histogram, it will be really pleasing to eyes if you find it in this way, right? In fact, most of the students want the histogram to be in this kind of a format.
Exactly, but unfortunately, normal is only theoretical. We do a lot of tests and assuming stuff to be normal because that is something that all statisticians love. But in real life, when the data is extremely large, then you can start assuming it to be normal, but it need not be the case. Yeah, but like you said, Swami, distribution like this, where you have a peak and then buildings around it and then something on the side, it's always appeasing to the eye.
Sure. So next, let's have a look at the basic descriptive stats. The mean seems to be 56.95 and the standard deviation is relatively low. So we have around 14.87 as standard deviation. So the minimum value is 27 and the maximum value is 101 and the median is 56.
Yeah,
so
1 second, Swami.
Yeah.
There's something interesting in this particular summary statistics, which is if you see between 27 and 48, the minimum and the 25th quantile, it's around 20. All right.
Yeah.
Between 25 and 50, it's around 10.
Yeah.
And 50 to 75, another 10. Whereas from 75 to the maximum, it's more than 30, which means there's a tail on the right side.
Fantastic. Yeah. And the other interesting thing is mean and median.
Median are almost same, which means it's symmetric.
Yeah.
So there's huge symmetry with a slight tail. So that is what the summary statistics, if you look at it along with the histogram, you can actually derive a lot of insights from them. Visual insights. Whatever your visualization is actually being concreted by these statistics.
Great. So let's also look at the important parameters like skewness and kurtosis. And skewness seems to be 0.37 and kurtosis is 0.6.
So whenever you have a positive skew, it means the distribution is right tail. Values are more than the mean.
Yes.
So everything is now falling into place. Whatever we observed, whatever we thought our descriptive statistics is actually reinforcing our visualization, that is also now reinforced by statistical concepts of skewness and kurtosis.
Beautiful. So the next step is again median, which we already got it from the descriptive stats. Again, it's 56. May not be of much help now. So again, we'll download the required packages. Next is the QQ plot. So let's see how the QQ plot looks like. And as usual, we have the DF of observation, which is the data set. And we don't have anything to compare it with because by default, it is going to compare with the normal distribution.
It's going to compare with the standard normal distribution.
Yeah.
So in this case, what the code actually does is it converts the data that is fed to it to a standard normal. It will scale it basically by doing x minus mu by sigma. It will scale it and then it will compare it with the standard normal and see how the quantiles are fitting.
Yes.
So that is what
the right word to use is normalizing. So it will normalize the data.
Yeah. Yeah. So that is the terminology that I should have used. So it will normalize the data and then compare it with the standard normal.
Beautiful.
So if you see, this is a perfect fit. You will not get a more better fit in real life scenarios. So this is actually a perfect fit, and the QQ plot says that it is a normal distribution.
Very true. So let's also look at the story behind the probability plot or PP plot.
And
Similar?
yeah, exactly the same thing. So PP plot is comparing it with the CDF. QQ plot is comparing the quantiles, and both are telling the same thing. So it is a normal distribution.
We can close our guess now. So let's call it normal distribution for now.
We can call it, yeah. The further steps, in fact, that we are going to do after getting all of these, we can actually 95% say it's normal and no one will question you. But just for the sake of that 5% who will say, no, I want that statistic, we will go and show how to do a chi-squared test for this particular data set.
Got it. So now let's split this data into 6 equal intervals. For example, let's say we have a normal curve. So let's divide it into 6 equal intervals. So as you all know, the area under the curve is 1. So if you divide it by 6, the area under each bucket will be around 0.166 or 0.167, right? Yeah. So this is what I have chosen to divide the data into 6 intervals. So therefore, I'm using n as 1 by 6.
And you can use any number. You can divide it by 7, 8, 9, whatever. And accordingly, a future, we'll tell you how to change the code. Yeah. For now, we are doing 6.
So another usual formality, import scipy.stats. So now what I'm doing is, I'm actually using this term called scipy.stats.norm.ppf. Remember, we calculated the Poisson probability using a similar function. So similarly, I'm using this for the normal distribution where I have the number of classes here, which is 6. And then I have the parameters of normal distribution, which are nothing but mean and standard deviation.
They are using 2 parameters for that normal, yes.
Which is mean and standard deviation. And then let's print this variable called probability intervals. So we had divided this into 6 equal intervals for which I'm calculating the probability intervals, right? So right now we have around 5 values. So which means that we can split the data, say below 42 to 42 in one bucket, 42 to 50.55 in the second bucket, 50.55 to 56.95 in the third bucket, and then 56.95 to 63.36 in the next bucket, and 63.36 to 71.34 in the last bucket or the 6th bucket, right? And if you calculate it manually, so you will see the observed frequency, which is 97979797. So we can say that between, less than 42.51 to 42.57, we had 9 observations.
Okay. So as an exercise, maybe students can open the Excel file and do a filter. We don't have to do it, Swami. Let the students do it to just check whether our numbers are right. So they can open the Excel file, put a filter, go to the numerical filters.
Okay.
No. Yeah. Okay.
Let us do it for one so that people understand it better.
All right, fine. Fair enough. If you can add a filter.
Okay. So now let me also arrange it in ascending order, right? So we saw this interval 42.57.
57.
So if you look at this, so there'll be 9 observations.
Exactly.
And let us take a look at the next 7 observations. So you have till,
50.
you have from 45 to 50, right? So that's the second bucket. 42 to 50 is the second bucket. So likewise, we have created 6 buckets and we have the observed frequency as 9, 7, 9, 7, 9, 7, and so on. So since we are splitting this into 6 buckets, so we told you that I'm taking n as 1 by 6, and we had 48 observations. So which means the expected frequency under each bucket is nothing but 48 divided by 6, which is 8.
Exactly.
So that's why I have the expected frequency as 8 under each bucket, right? So we have 2 lists. One is expected frequency, other one is the observed frequency. So as usual, let's get into the chi-square test between the observed frequency and the expected frequency. So again, we have a p-value of 0.9948. It's a very strong p-value.
Which is very greater than 0.05, 0.1, or 0.15, whichever alpha value you want to use. So you will, at this point, according to p-value, you can say that you do not reject the null hypothesis. And what is the null hypothesis? Take a pause. Yeah, so the null hypothesis is going to be that the observed sample is following a normal distribution. And the alternative is that it is not following a normal distribution. So since the p-value is 0.99, which is greater than your alpha, you are going to conclude saying that, yes, this distribution follows a normal.
Okay, so hold on the suspense. We have another question for you. So let's also confirm this using the calculated value and tabulated value of the chi-square statistic. As you all know, the calculated value of chi-square statistic is 1.0. What should be the tabulated value of chi-square statistic? Should it be greater or lesser? So that's up to you. So we already have a calculated chi-square statistic of 1.0. So now let's check it with the tabulated value of chi-square statistic, for which I'm using this library called scipy.stats, and the syntax is chi-square.tpf. And we have 2 parameters or 2 arguments. One is 0.95 and other is 3, where 0.95 is the confidence level, say 95%, and then 3 is nothing but the degrees of freedom. And Malo, would you talk about the degrees of freedom?
So the degrees of freedom is basically going to be k minus p minus 1. So k is the number of buckets. So we used 6 intervals. So it is 6 minus 1, which is 5, minus p. P is the number of parameters we compute from the sample. So in this case, for a normal, we need the mean and the variance. So we have computed 2 parameters. So 6 minus 2 minus 1, which is 3. So chi-squared of 0.95, comma 3. And the value for that is 7.8, which means since 7.8 is greater than 1, we do not reject the null hypothesis, and hence this is coming from a normal population
distribution.
Yeah.
Hello, would you also like to talk about the business cases of normal distribution?
Sure. When we talk about normal, most of our life events can be assumed to be normal. One such thing, all of us would have taken a test. So our test scores over the years could be a normal distribution, or test scores of an entire class will be normally distributed. So those are all real life examples of a normal distribution. Anything else from your end, Swami? Can you think of something?
So in fact, if you look at this data, which I got, so this comes from automotive sales. So there were around 48 salesmen who have sold tractors on a particular month. So ideally, you will see a couple of people who are performing extremely well, and there'll be some salesmen who may not be performing well. And in between, you will have the majority of people. So that's again a beautiful example for normal distribution.
Exactly.
All right, with this, we conclude this tutorial on normal distribution.